KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class, we start with particle nature of light. Okay, right? That's started in the previous class, right? So from starting off this dual nature of light, regarding the Neet classes, this is the fourth class, right? So in our previous classes, we discussed what is photoelectric effect, what is work function, and what is threshold frequency. Next, what is threshold wavelength. So these three are the important definitions I already told you. Those are work function, threshold frequency, threshold wavelength. Afterwards, we discussed Hedge observations. Next, Hallmarks and Leonard observations. Right. After completion of these things, we discussed what is Einstein photoelectric equation. That is what capital E is equal to W naught, capital E is equal to W naught plus K maximum. Capital E is the energy of the incident radiation, W naught is the work function, and K maximum is the maximum kinetic energy of the emitted electrons, right? So this is what Einstein's photoelectric equation. After completion of that, we focused on what is the effect of intensity and what is the effect of frequency, right? So after that, we discussed important formula for photoelectric effect, Thereafter, we started, matter waves, that is what de Broglie waves, you can also call them as de Broglie waves. And there itself, we have to discuss two things. One is particle nature of light, another one is wave nature of light, right? So we started particle nature of light yesterday. So from there onwards, we will continue this class. Okay. So what is photon also we discussed, right? So in the particle nature of light, and what is photon also we discussed. Okay, right. So till now, whatever we discussed, from that information, we have to keep in mind what is work function. So work function is nothing but minimum energy of incident radiation required to eject the electrons from metallic surface. Okay, right. And what is threshold frequency means the minimum frequency of incident radiation required to eject the electron from metallic surface. Next, threshold wavelength is nothing but the maximum wavelength of incident radiations required to eject the electrons from a metallic surface. Okay, right. So afterwards, we discuss the scenario, that is what happened in case of Hedge observations, and then Hallmark and Leonard observations. Right. Thereafter, E is equal to W naught plus K maximum is the Einstein's photoelectric equation. Okay. If you see the relation between, that is what, photocurrent and intensity. Okay. And if you observe carefully, in case of intensity of light is increased, the current levels, right? So the current levels half at a higher value, showing that more electrons are being emitted per unit time. okay, but the stopping potential doesn't change. That is what you can say one important relation. That is what intensity is directly proportional to the number of incident photons, is directly proportional to the number of emitted photoelectrons per time, is directly proportional to the photocurrent, is directly proportional to the 1 by distance whole square. Okay, and the graphs also we have shown in our previous class. Then effect of frequency. If a frequency of incident light increases, stopping potential increases, but there is no change in the photoelectric current. There is no change in the photoelectric current. Okay, that. But our discussion is, when we talk about effect of frequency, intensity kept constant. Intensity kept constant, right? When we talked about intensity, that is what effect of intensity, frequency kept constant. Okay, right. Afterwards, we discussed some important formulas. All the formulas are important for our Neet and JEE mains point of view. Okay, right. So afterwards, I explained you matter waves. According to de Broglie, a moving material particle sometimes acts as a wave and sometimes as a particle. Okay, right. The wave associated with moving particle is called matter wave or de Broglie wave. The wave associated with moving particle is called matter wave or de Broglie wave, and it propagates in the form of wave packets with group velocity. Okay, that is what the fact what I told you. And next I started particle nature of light, right? So this class is also particle nature of light only, So from here to that next I'll tell you up to that wave nature of light, our discussion is completely, our focus is completely on particle nature of light. So when we are going to discuss about particle nature of light, first and foremost thing is, what is photon? What is photon? Okay, right. According to Einstein's quantum theory of light, okay, according to Einstein's quantum theory, light propagates in the form of bundles of energy. So this bundles means, like pockets or quanta. Okay, so according to Einstein's quantum theory, light propagates in the form of bundles of energy. Each bundle is called a photon and possessing energy. Each bundle is called a photon and possessing energy. Okay, right. Next, we start with this class. That is what, what is the energy of the photon? What is the, okay, right, according to Einstein's, that is what quantum theory of light, okay, light propagates in the form of bundles of energy, right? Each bundle is called a photon and possessing energy, right? So what is the energy of the photon? You see this formula, that is what energy of photon is given by E is equal to h nu, that is equal to hc by lambda, right? Very well, that is what c is the speed of light and h is the Planck's constant, and this is the value of the Planck's constant, that is 6.6 into 10 to the power of minus 34 joule second. Next, v is nu is frequency, that is in hertz, right? Next, lambda is the wavelength of light. Lambda is the, here lambda is there, no? Okay, I didn't write here, but I hope you understood what is lambda, right? Because we used many times. Lambda is wavelength of light. Okay, right. Next, the same thing, if you want to write in electron volt, the same thing, that is what, if you want to write in electron volt, in electron volt, E is equal to hc by E lambda, hc by E lambda, and the product of this is, that is what, Planck's constant and speed of light. Speed of light is equal to 12375, right? And approximately you can take it as 12,400, 12,400, and the denominator is like wavelength, in angstrom unit, in angstrom unit. Okay, right. Next, mass of a photon. Mass of a photon, right? So mass of photon, see here. Actually, rest mass of the photon is 0. Actually, rest mass of the photon is 0. But its effective mass is given by, its effective mass is given by, or its effective mass is given as, E is equal to mc square, the formula, Einstein's formula, and is equal to h nu. So what is the mass of the photon, ma? Just mathematically you think of that. So E by c square, generally, that you can also write it as h nu by c square. H nu by c square, that is equal to h by c lambda. H by c lambda, because c is equal to nu lambda, no? So nu is equal to c by lambda and h by c lambda. H by c lambda, and this mass is also kinetic mass of the photon. This mass is also kinetic mass of the photon. Can you understand why he is calling kinetic mass of the photon? Because this mass is present with motion. This mass is present due to the motion, right? So when the photon is at rest, its mass is 0. That is what actually the rest mass of the photon is 0, right? So because of that, because of the situation, he is calling with that name, kinetic mass of the photon. Kinetic mass of the photon. Okay, right. Next, momentum of the photon. You know that momentum is the product of mass and velocity or speed, which is m into c is equal to, so from this relation you can write it as E by c. E by c means you can write it as h nu by c. You can write it as h by lambda. H nu by c, that is equal to h by lambda. P is equal to m into c, that is equal to E by c, that is equal to h nu by c, that is equal to h by lambda. H by lambda. Okay, right. And next, number of emitted photons. A number of emitted photons. Okay, right. See this. The number of photons emitted per second. The number of photons emitted per second from a source of monochromatic radiation of wavelength lambda and power. The number of photons emitted per second. The number of photons emitted per second from a source of monochromatic radiation. From a source of monochromatic radiation of wavelength lambda, and power is given as, n is equal to, small n is equal to p by e, that is equal to p by h nu, that is equal to p lambda by hc. P lambda by hc. Okay, that is what we can write it as mathematically, because E is equal to h nu, that is equal to hc by lambda, right? The same thing we are writing in terms of different physical quantities. For example, if we have only the power and what is energy, this is the formula, that is what P by E. Suppose you have that is what h and nu, that is Planck's constant and frequency, means you can write this formula P by h nu. Suppose power and wavelength and speed of light, and then that is what Planck's constant. Planck's constant, then I can use this formula, that is what P lambda by hc. P lambda by hc. Okay, right. Next, see here, intensity of light. Intensity of light. See this. Energy crossing per unit area. Energy crossing per unit area normally per second. Energy crossing per unit area normally per second is called intensity or energy flux. Energy crossing per unit area normally per second is called intensity or energy flux. I is equal to E by A into T, that is equal to P by A, because E by A is equal, that is what see here, right? And from this one and here also we used, that is what, okay, right, this is what power. Energy crossing unit area is called intensity, that is what energy flux, no, right? So I is equal to E by A into T, that is equal to P by A. So why P by A means this is what radiation power. Radiation power P is equal to E by T. So in place of E by T he put P, right? At a distance small r from a point source of power. At a distance small r from a point source of power P, intensity is given by I is equal, same formula, I is equal to P by A, But in place of A, he is writing 4 pi r square. 4 pi r square. Okay. From this relation, you can see that is what I is directly proportional to 1 by r square. I is directly proportional to 1 by r square, and for a line source, it is I is directly proportional to 1 by small r. I is directly proportional to 1 by small r. Okay, right. Next, number of photons falling per second. Number of photon falling per second n is, that is what if P is the power of radiation and E is the energy of a photon, right? If P is the power of radiation and E is the energy of a photon, then n is equal to P by E. N is equal to P by E. This we already discussed, but once again I am repeating, right? Once again I repeated, that is what n is equal to P by E. N is equal to P by E. P is the power and E is the energy. Okay, right. Next, so till now, from starting of, that is what from the ending of the previous class, that is what where we started particle nature of light, till here we discussed about particle nature of light only. In particle nature of light, what is the energy of the each photon, otherwise energy of photon, and what is the mass of the photon, and what is the momentum of the photon, and what about the number of emitted photons, and then what is the intensity of light, what is the intensity of the light, and then afterwards I is directly okay, that is what based on the situation, and at last number of photon falling per second, number of photon falling per second also we discussed in the particle nature of light. Now we are going to concentrate on wave nature of light. Okay, so both the things we are in a discussion in the chapter of dual nature of light. Okay, right. See here, here every line is important, so when I am going through line by line, you have to get the imagination what is there. Okay, that is very important for us in physics. Imagination and visualization, the situation is very important. Okay, and what is particle nature of light means, at the starting of the particle nature of light, I told you, according to Einstein's quantum theory, light propagates in the form of bundles of energy. So that bundle is called as, each bundle is called as one pocket, otherwise quanta. Okay, that's what I want to say. And each photon has certain amount of energy, because light is a form of invisible energy. Light is a form of invisible energy. So whatever the energy possessed by a light, it has to share by the photons, right? So that you can say that even thinking logically also, you can say that photon has certain amount of energy. That also we calculated by using that formula, E is equal to h nu, that is equal to hc by lambda. That is equal to hc by lambda. Okay, right. See here. Now we are going to concentrate on wave nature of light. Listen here what he is saying, right? It is an established fact that radiation has a dual aspect, behaving either as waves or particles under suitable circumstances, right? This is the fact. The name of the chapter is dual nature of light. So in this chapter we are in a discussion about both the particle nature of light and wave nature of light. Okay, see here, it is an established fact. Try to understand the meaning of the word established fact. It is an established fact that radiation has a dual aspect, behaving either as waves or as particles under suitable circumstances. Okay, right, full stop. Right, next. A particle having a finite mass, has been supposed to be associated. A particle having a finite mass has been supposed to be associated with a definite amount of energy, given by Einstein in his mass energy relationship. E is equal to mc square. E is equal to mc square. Where E is the energy associated with a particle of mass m and c is being the velocity of light. On the basis, a wave has a particle aspect. A wave has a particle aspect, right? I will repeat once again, you just focus from here onwards. That is what a particle having a finite mass has been supposed to be associated with a definite amount of energy given by Einstein in his mass energy relationship. That is what E is equal to mc square. So what is E? Energy associated with a particle of mass m, right? And here itself we got it, m is the mass of the particle, right? So that is what the particle of mass m. And what is C? It is the velocity of light. Velocity of light. On the basis, a wave has a particle aspect. A wave has a particle aspect. Okay, right. And next, see, in the year of 1924, it was argued by de Broglie. In the year of 1924, it was argued by de Broglie that if radiation has a dual aspect, why not think of particles of matter also having dual aspects, right? If radiation has dual aspect, why not think of particles of matter also has this dual aspect? So the question mark, right? So the answer is, here itself we have answer, see here. Nature loves symmetry. Nature loves symmetry, and if mass energy symmetry is present for waves, and if mass energy is present for waves, then the same symmetry should be also available for a material particles. So whatever the E is equal to mc square formula we have for particles, according to the natural symmetry, the nature symmetry, according to the symmetric pattern, right? The material particles also satisfies the same formula, that is E is equal to mc square. Okay, right. In simple words, what we know as material particles should also behave like waves of a definite wavelength under suitable conditions. Okay, so what we know, in simple words, what we know a material particles means what, electrons, protons, neutrons, like that. Okay, in simple words, what we know as a material particles like electrons, protons and neutrons should also behave like waves of a definite wavelength under suitable conditions, full stop. Thus particles may also behave as waves. This is the dual nature of matter. Right? So dual nature of matter means what? So matter also having, that is what, particle nature. See here, thus particles may also behave as waves. Okay, so matter also experiencing dual nature. That is what here he is saying clearly. That is what, see here, So in simple words, what we know as material particles should also behave like waves of a definite wavelength under suitable conditions. Thus particle may also behave as waves. See here, thus particles may also behave as waves. This is a dual nature of matter. Okay, the waves which are associated with matter are called matter waves or de Broglie waves. The waves which are associated with matter are called matter waves or de Broglie waves, right? After the name of the French scientist who gave us this idea, right? So to honor the name of the scientist, we kept his name as a type of waves, that is what, matter waves or de Broglie waves. Matter waves or de Broglie waves. Okay, right. And here is no space, that's why I am saying some of the information. You just keep in mind, right? So after completion of this, that is what the experiments performed later on the actually proved the duality of matter. After completion of this, some of the experiments has gone through, and the experiments performed later and proved the duality of matter. Okay, and we know that electrons are particles having a discrete mass and moving with a definite velocity. Regarding the electrons, right? Regarding the electrons, a discrete mass and moving with a definite velocity. Sometimes these behave like waves and produce diffraction pattern as shown by the scientists Davison and Germer, and also by Thomson. Okay, so the concept of de Broglie waves is not purely the flight of fancy of a scientist, but actually in existence, right? So we accept this duality of matter as we accept the duality of radiation, right? So how we are accepting the duality of radiation? Similarly we are expecting duality of radiation. Okay, and it has to be noted that Bohr's law complementary holds good here, right? And this means that in no experiment matter exists both as a particle as a wave simultaneously, right? It is either one or the other aspect, and not this and not that aspect together. So that is what so the two aspects, wave and particle, are complementary to each other, right? So need not to say more, because how radiation has dual nature, we know, right? That we are getting from, that is what in the ray optics chapter, in the wave optics chapter, right? We got it because light, right? So it's electromagnetic radiation. Similarly, matter also behaves. So whatever the de Broglie thought, once idea is satisfied, and the consequences, what the radiation satisfied and followed, the same thing the material particle or the matter also doing the same thing. Okay, so that's what in this class. So in this class we discussed particle nature of light and important definitions: energy, mass, momentum, number of emitted photons, intensity of light. Okay, so this all belongs to the particle nature of light. Afterwards we discussed wave nature of light. Okay, right. Thank you. We will continue in the next class.